Picture a metal cylinder the size of a London double-decker bus, spinning fast enough to gulp down more than a ton of air every second. Now, attach 4 of them to the wings of a jet that carries an entire small town at 900 kilometers per hour. Welcome to the Rolls-Royce Trent 900, one of 2 engines that power the Airbus A380. Today, you will see how engineers turn raw titanium, nickel superalloys, and space-age ceramics into 80,000 pounds of pure thrust. In the heart of a modern jet engine, just behind the combustion chamber, lies the most hostile environment ever engineered by man. Here, the air reaches temperatures of over 1,600 degrees Celsius, or 3,000 degrees Fahrenheit. This is hundreds of degrees hotter than the melting point of the very metal used to build the engine. If you were to place a standard block of steel in this flow, it would turn into a puddle in seconds. Yet, the turbine blades spinning at 12,000 RPM stay solid, flight after flight. Today we are going inside the world's elite aerospace foundries to witness the 2,000 degrees Fahrenheit flow. We are exploring how engineers grow single crystal turbine blades to survive temperatures that should be physically impossible. The superalloy, nickel's secret. And the journey begins in the metallurgy lab. To survive the hot section of a jet engine, you cannot use titanium or steel. They simply aren't stable enough at high heat. Instead, we use nickel-based superalloys. These are exotic blends of nickel, cobalt, and rare earth elements like rhenium and ruthenium. At process sector, we look at the atomic lattice. At extreme temperatures, most metals suffer from creep, a slow, permanent deformation, where the metal atoms begin to slide past one another. To prevent this, these superalloys are designed with a specific gamma-prime microstructure that locks the atoms in place. But even the best alloy has a weakness: grain boundaries. In a normal piece of metal, tiny individual crystals meet at borders. At 1200 degrees Celsius, these borders become liquid-like, and the blade will stretch and eventually shatter. The solution? Eliminate the borders. Investment casting, the lost wax masterpiece. Manufacturing a turbine blade starts with investment casting. First, a high-precision metal die is used to inject specialized wax, creating a perfect replica of the blade. But this isn't just a solid shape. Inside the wax, technicians place a ceramic core. This core is a complex, fragile sculpture that will eventually form the internal cooling veins of the blade. These wax patterns are then assembled into a tree or cluster. The tree is dipped repeatedly into a ceramic slurry and coated in fine sand. This process is repeated up to a dozen times over several days until a thick, rock-hard shell is formed. The assembly is then placed in an autoclave, where the wax is melted out, leaving behind a hollow ceramic investment that is a perfect negative of the engine parts. The single crystal growth, growing a diamond of metal. This is the most critical stage in the process sector of aviation. The hollow ceramic molds are placed inside a vacuum induction melting (VIM) furnace. In the vacuum, the superalloy is melted to 1500 degrees Celsius to ensure no oxygen can contaminate the metal. But the real magic happens in the withdrawal chamber. At the bottom of the mold is a grain selector, a pigtail-shaped spiral of ceramic. As the molten metal begins to cool, hundreds of tiny crystals start to grow at the bottom. As they travel up the spiral, only one crystal, the one with the most perfect orientation, can navigate the curves. The mold is then slowly withdrawn from the heat at a rate of just a few millimeters per hour. This directional solidification allows one single crystal to grow upward, filling the entire mold. The result is a turbine blade that is technically a single massive metallic crystal. Because there are no grain boundaries, there is nowhere for the metal to creep or fail. The entire blade is essentially as structurally sound as a giant industrial diamond. The internal labyrinth, cooling from the inside out. Once the metal has solidified, the ceramic shell is hammered away. To remove the ceramic core trapped inside the metal, the blades are placed in a chemical bath of hot caustic soda, which leaches the ceramic out, leaving behind a hollow labyrinth. This internal structure is what keeps the blade from melting. On using air bled from the engine's compressor, cool air is pumped into the base of the blade. It travels through the internal maze and exits through thousands of microscopic laser-drilled holes on the surface. This creates a film cooling effect, which is a thin, protective boundary layer of cool air at 700 degrees Celsius that sits between the 1600-degree exhaust gas and the metal surface. At process sector, we call this the air shield. It is the only reason the metal doesn't vaporize. If the cooling holes, some as small as a human hair, become clogged with dust or volcanic ash, the blade will melt within minutes. Thermal barrier coatings, the ceramic skin. The final defense is a thermal barrier coating, TBC. The blades are placed in a physical vapor deposition, PVD chamber. An electron beam hits a ceramic ingot, usually yttria-stabilized zirconia, turning it into a gas. This gas settles on the spinning turbine blades, creating a feathered ceramic coating. This ceramic layer has extremely low thermal conductivity. It acts like the heat shield on a space shuttle, providing a temperature drop of up to 300 degrees Celsius across a layer thinner than a credit card. Without this skin, the engine could never reach the efficiencies required for modern long-haul flight. The zero-tolerance inspection. Because a single blade failure can destroy an entire engine, the inspection process sector is brutal. Every blade undergoes X-ray defectoscopy to look for internal voids or cracks. Fluorescent penetrant inspection, FPI, using UV light to find microscopic surface fractures. Laowa back reflection, a specialized X-ray technique to confirm that the entire blade is, in fact, one single crystal. If even a tiny secondary grain is found, the $15,000 blade is scrapped. The physics-defying machine. A modern jet engine is more than just a turbine. It is a testament to our ability to manipulate the very atoms of the Earth. We take sand and rare metals, melt them in a vacuum, and grow them into a single crystal that can withstand forces and temperatures that would destroy anything else in nature. The 2000 degrees Fahrenheit flow is the ultimate frontier of manufacturing. Every time you look out of a plane window at the engine cowling, remember the white-hot foundries and the microscopic laser holes. You are being pushed through the sky by a collection of grown crystals, cooled by an invisible shield of air. We know that the higher we fly, the more we rely on the perfection of the process.